welcome everybody. This is the 6th lecture, and today we will talk about non-deterministic finite automata. So, I will begin by reviewing the differences between a deterministic finite automaton and a non-deterministic finite automaton. Then I will give the formal definition of what a non-deterministic finite automaton is and what does it mean, what is the definition of computation by a non-deterministic finite automaton, and I will end with a few examples. So, let us look at some differences. So, we have DFA and we have NFA. Okay. So, the first is in a DFA from a state comma symbol pair. Okay. So, from let us say a state comma symbol pair, we go to a single state always. So, this is the most important feature, whereas in the case of an NFA from a state comma symbol pair, we can go to multiple states. Okay. The second point is in a DFA we have a single computation that is happening. Okay. So, there is one way of thinking of it is that, so if you think of the clone model that I talked about last time, in the case of a DFA there is only one person. Okay. So, this person who is actually working on this automaton is more like a person from our planet. Okay. So, it does not create any clones of himself or herself. At every point of the computation, it reads the next input bit and it moves to the next state. So, there is a single computation that is happening. In the case of an NFA, we have multiple computations that are happening simultaneously. Okay. So, because of this fact that from one state we can go to multiple states and each of those computations can proceed independent of one another in a simultaneous manner, we have multiple different computations. The third point is that of epsilon transition. So, in a DFA we do not have any epsilon transitions. By definition, here we have epsilon transitions. The next point is that of acceptance. In the case of a DFA, the definition of acceptance is pretty simple because there is only one computation path. So, at the end either you are at an accept state or you are at a you are not at an accept state. So, you are if you are at an accept state, then you accept, otherwise you do not. So, here accept if the computation ends at an accept state. In the case of a non-deterministic finite automaton, the definition is different. So, here we accept if one of the computation paths ends up at an accept state. Okay. So, these are the fundamental differences. So, just the complement fact is that when do we reject an input? Again, in the case of a DFA, we reject an input if the unique computation path ends up at a non-accept state. Here we will reject the input if none of the computation paths end up at an accept state. So, basically all the computation paths end up at a non-accept state. Okay. So, now let us formally define what an NFA is. So, a non-deterministic finite automaton, which in short we call a NFA, is the five tuple n equals q sigma delta q naught comma f. So, once again we have a 5 tuple and basically except for the transition function, which is slightly different in the case of an NFA, the other symbols are basically they denote the same thing. So, where q is the finite set of states, sigma is the input alphabet. I will just come to the transition function in a moment. Q naught is the start state and F is the set of accept states. So, what is the transition function? How is the transition function defined here? So, let us recall how transition happens in the case of an NFA. In the case of a DFA, from one state on a input symbol we go to a unique state. So, therefore, it was a map from q cross sigma to the set q itself, because we went to a single state. In the case of an NFA, from a state comma symbol pair we can go to multiple states, okay, and that can include the empty set as well. Okay. So, in the case of an NFA we have transitions which go from q cross sigma. So, it is a function from q cross sigma to the power set of q, basically the set of all subsets of q. Okay. So, this we denote as 2 to the power q, and this is not it. Okay. So, this is not complete, because also in the case of an NFA we have epsilon transitions. Okay. So, we need to accommodate for that as well. Okay. So, from a state q we can see a symbol which is from the input alphabet, or we can also see a epsilon transition. Okay. So, instead of sigma we will write it as sigma epsilon. Okay. So, let me just for the sake of completeness, let me write this. So, recall that sigma epsilon is basically sigma together with the symbol epsilon, and for a set A 2 raised to the power A denotes the power set of A. Okay. So, this is what is the definition of an NFA. Now, how do we define acceptance? Okay. So, let us say we have this NFA. Okay. So, this was the definition of a non-deterministic finite automata. We say that n accepts an input W which is equal to, let us say, A1, A2 up to An. Okay. So, let us say we have a string W which has n symbols in it, A1 through n. When do we say that a non-deterministic finite automaton accepts W? So, we say that n accepts A1 W if we can write W as W equals B1, B2 up to some Bm, where Bi's belong to sigma epsilon, and there exists a sequence of states R0, R1 up to Rm, not necessarily distinct. Okay. Such that so before I complete this, let us try to parse what we have written so far. So, suppose I have a string W which is A1 through An. We say that our non-deterministic automaton accepts W if I can write W as a sequence of symbols B1 through Bm, where these Bi's come from sigma epsilon. Okay. So, some of these Bi's can also be the epsilon symbol. Okay. So, in other words, if I just concatenate all these symbols, I will get W. Okay. So, I have some extra epsilons over here, and there is a sequence of states R0 up to Rm. Okay. So, one point that needs to be noted here is that note that here I have n and here I have m, and of course, m is a number that is greater than or equal to n, because I have these additional epsilon symbols plugged in between. Okay. So, we have this sequence of states R0 to Rm, and these states are not necessarily distinct. So, some of these states can be the same state, such that we first we have to write the initial condition, that is R0 equals Q0. Okay. So, this is the initial condition. Secondly, what is the transition condition here? How can we go from a state Ri to a state Ri plus 1? So, Ri is contained in delta of Ri minus 1 comma Bi, okay, for all I going from 1 through m. So, this is the transition condition. Okay. So, there are two important points here. The first point is that note that we have a is element of sign over here, because this by definition what we have on the right hand side is a set of states, okay, because in the case of a non-deterministic finite automata, given a state and a symbol, it produces a set. Okay. So, we have a set on the right hand side. So, if Ri belongs to this set, then we say that the automaton goes from Ri minus 1 to Ri in the next step. Okay. And the second point is, so Ri is basically just some element. Okay. There may be other elements in this set which are not Ri, which may be some other element, basically which just means that it is just a different computation path. Okay. And finally, we must write the acceptance condition. So, we accept if R m belongs to F. Okay. So, this is when we accept the input. So, now with this definition, we are ready to define the language of a non-deterministic finite automaton. So, L of n is the set of all strings W in sigma star such that n accepts W. Okay. So, this is the definition of the language of a non-deterministic finite automaton. Okay. So, now let us look at a couple of examples of non-deterministic automata. So, consider the language L1, which is set of all strings W over 0 ones, such that the third last symbol of W is a 1. Okay. So, I want to look at all those strings whose third last symbol must be a 1. I do not care about the last two symbols, nor do I care about the first n minus 3 symbols. Okay. How can we design a automaton for this? So, let us try to design a NFA, because we are studying about non-determinism. So, what we will do is, so we have our start state, let us call it Q0. So, what we do is from Q0, we try to do the following thing, try to do the following non-deterministically. So, at Q0, I will always try to guess non-deterministically whether the next symbol is the third last symbol or not. Okay, so there are two things that can happen. Either the next symbol is the third last symbol or it is not. So, if it is not the third last symbol, then I will just ignore it. So, I will stay at Q0 on a 0 or 1. If it is the third last symbol, then I will go to the state Q1 on a 1. Okay, so, if it is the third last symbol, I will go. Then again from Q1, I go to a state Q2 on seeing either 0 or 1, because if this is the third last symbol, this will be the second last symbol. I do not care what it is. And then from Q2, I go to a state Q3 again or a 0 or a 1. This is the last symbol and this is my accept state. Okay. Now, let us look at some examples. So, let us say that I have a string 0, 1, 1, 0. Okay. So, how does computation proceed for this string on this automaton? So, maybe just change this. Let us say I have a string 1, 1, 1, 0. So, in this, for this string, the third last symbol is this one, which is a 1, which means that this should be accepted. So, what happens when we see this string? So, let us try to create a table as we had done last time. So, when I see the first one, I go to both these states Q0 and Q1. Okay. So, when I see 1, I go to from Q0 on seeing 1, we go to both Q0 and Q1. Going to Q0 essentially means that I am guessing that the symbol that I am currently reading, which is 1, is not the third last symbol, and going to Q1 means that I am guessing that it is the third last symbol. Okay. So, I am using non-determinism to do two things. So, I am creating a clone of myself, and one clone I am telling one clone that, well, the bit that I am reading is the third last bit, act accordingly, and to the other clone I am saying that it is not the third last bit, you should also act accordingly. Now, from Q0, Q1 on seeing the next one, where do we go to? Okay. So, again from Q0 we go to Q0 and Q1, and from Q1 we go to Q2. So, we go to Q0, Q1 and Q2. Okay. On seeing the third one, we go to, again from Q0 we go to Q0 and Q1. From Q1 we go to Q2, and from Q2 we go to Q3. Okay, so, although we have got an accept state, we cannot stop here because the input is not completely read. Now, the last bit is a 0. So, what happens when we read a 0? So, on a 0 from Q0 we go to Q0 itself, from Q1 we will go to Q2, and so let us write it down. So, on seeing 0, from Q0 we stay at Q0, from Q1 we go to Q2, and from Q3 from Q2 we go to Q3, okay, and from Q3 we do not go anywhere. So, again that computation also dies out. So, this is the final set of states, and because Q3 is one of the accept states in the final set, hence I accept the input. Okay. Now, if you take another example, so this is one example. If you take another example where the third last bit is not a 1, let us say 1, 0, 1, 0, and if you just carry out this computation, you will realize at the end, you should just try this out, that you will not get Q3 in the final set of states, okay, which means that this input will not get accepted. So, this is an example of an NFA for this language. So, the question is, why do we construct an NFA for this language, or in other words, can we construct a DFA for this language? Okay. So, as a exercise you can try to show that there exists a DFA for this language L as well, and you can try to analyze how many states do you need, what is the minimum number of states in the DFA you need that would accept L. Okay. And in general what you can try is that if you consider a language LK which is set of all strings over 0 1 such that the kth last bit is a 1. If you try to construct an NFA for it using the same logic, you will figure, I mean you will realize that you can actually do this using just k plus 1 states, okay, using the same idea. But again just try doing try constructing a DFA for this language and then try to find out what is the minimum number of states that you need, okay. And then you can try to compare these two numbers, I mean, okay, and see that what kind of advantage NFA gives. So, let us look at another example. Okay. So, this time we will look at a unary language, a language over just one alphabet. So, let's look at the set of all strings over a single alphabet 0 such that the length of W is divisible by 2 or by 7. Okay. So, how can you create an NFA for strings whose length is divisible either by 2 or let us instead of 7, let us maybe take 5 easier, 2 or by 5. Okay. So, here we will use epsilon transition to differentiate between these two ideas. So, we start at a start state q0 and from q0 we non-deterministically decide what are we going to check. So, are we going to check whether the length is divisible by 2 or are we going to check whether the length is divisible by 5. So, if we are going to check whether the length is divisible by 2, what we need to do is we just have a automaton like this. On a 0 we go to this state. Okay, so, let us call this as q1 and q2 and q1 is our accept state. Okay. So, here if the number of zeros is even, I will be at q1, and the second case I will basically have a 5 cycle okay, with this being the accept state that checks whether the number of zeros is divisible by 5 or not. So, if the number of zeros is divisible by 5, then it would end at this state, otherwise not. Okay. So, I am using epsilon transition to decide what I am going to check, whether divisibility by 2 or divisibility by 5. Okay. Thank you.